Hi everyone, my name is Dominic Scarcelli, and I'm going to be talking about some research that I conducted along with Dr. Mark Hogue of Slippery Rock University. Our research intended to look at students, calculus students, understanding of the tangent line, where it may originate from, and talking a little bit about what we can do to fix these misconceptions. So the main aims of our studies were to determine where these misconceptions of tangent lines originate. Also, we wanted to take a look at the various definitions that students give for tangent lines. And finally, we wanted to know what kind of role does definition play in students' misconceptions about this topic. So a very important theory that served to guide our study was the theory of the concept image and concept definition. Concept image, definition of the concept image is the total cognitive structure that is associated with the concept, which includes mental pictures, associated properties, and processes. So, the concept image, that's going to include things like a definition. It's also going to include examples of a concept. So, in our case, some examples of tangent lines, maybe a tangent line to a circle or a parabola, and maybe even in this case, students might have in their concept image the procedure for actually finding a tangent line. Now, the concept image is going to be different from the concept definition. The latter is defined as a form of words that is used, a form of words used to specify that concept. Now, for our study, we were particularly interested in students' personal concept definitions and how that affected their understandings of tangency. So, did students stick to their original definitions? Did their definitions change when they saw various examples of tangency? We wanted to know how that interaction would take place. So an important thing about definitions are that two definitions are said to be equivalent if the set of objects that fulfill or exemplify that definition are equal. So two definitions of tangency, for example, would be equal if every line that is tangent under one definition is tangent under the other definition, and vice versa. So the important thing to note here is that the only formal definition of tangency that's going to give a necessary and sufficient condition of tangency is the definition of the tangent line as a limiting position of secant lines that are passing through the point of tangency. However, students, especially students, often always will take other properties as the definition of a tangent line. So in calculus, now usually the limiting definition, the limiting position of secant lines is not used as the definition. Typically in calculus, we're only talking about tangent lines to differentiable functions, in which case the tangent line at some point x is going to be the line that is passing through that point on the function that has a slope equal to the derivative of the function at that point. And in certain cases, right, that definition and the limiting position of secant lines definition are going to align, right? And we can see that on the left here. If we're looking at this point here, P, if we take the limiting position of secant lines to that point, we can see that they approach, the standard tangent line that we would draw to that point. However, if we look on the right here at the cube root of x, if we try to find the tangent line at the origin using the calculus definition, well, this function is not differentiable at the origin, but it does have a limiting position of secant lines, and that would give us a vertical line. So the two definitions do not align when we're talking about functions that are not differentiable. Now, some other common properties of tangency that students, might give as necessary or maybe even necessary and sufficient conditions for tangency. One common one is that a tangent line will only have one point in common with the function. Another common one, a tangent line will only have one point in common with the function in some region around the point of tangency. So not necessarily on the whole domain, but at least on some region around the tangent point. Another common one, a tangent line should not cross over the function. Of course, that is not a true statement, but it is one that a lot of students believe is true. And finally, students might say, instead of saying that the tangent line never crosses over the function, they might say that it does not cross over the function at a point of tangency. So our methods in this study, we conducted one-on-one interviews in a semi-structured fashion. We had an assessment that we went through with the students. They would go through it. We would take a look at their answers. We would ask some follow-up questions as they were working, to clarify or to expand on a point. And then we took all that data and we looked for some common themes and attempted to relate our findings to past literature on the subject. So here's a couple of examples of questions from our assessment. The one on the left and on the middle, we asked the student whether those green lines were tangent to the function. The one on the left, of course, is a tangent line, while the one in the middle is not. The one on the right, we asked students to draw the tangent line to that function at point A. Now, looking at the one on the left, we would expect students who either don't accept tangent lines that cross over a function, or students that don't accept tangent lines that cross over a function at the point of tangency. We would expect those students to say that this is not a tangent line. For the one in the middle, this might be accepted as a tangent by a student who thinks that a tangent line is a line that only touches the function at a single point. The one on the right, if you were to draw the proper tangent here, it would just be horizontal passing through point A. And of course, we're going to have some students thinking that that should not be a tangent line because, well, it's going to coincide with the function to the left of that point. Now, in terms of our students' prior experiences with tangent lines, only about 4 of our 13 students had actually seen a tangent line in a math class prior to calculus. Now, some students did see tangent lines in other classes. For example, if we look here, we had some students who saw tangent lines in physics class or even in economics. In total, though, we had 5 students who had no encounters with tangent lines in any other class. Now, as for our students' initial conceptions on tangency, we had about 9 out of our 13 students holding kind of improper ideas about tangency that we would expect to see in maybe a geometry or algebra class. So, for example, saying that the tangent only touches at one point, like it would with a circle or a parabola, or saying that the tangent line does not cross over the function, again, like as would be the case with a circle or parabola. Now, 7 of our 13 students mentioned slope or derivative in their definition. All the students in this study were calculus students, so it is a bit surprising to see that only about half of them made any mention of slope or derivative at all. Now, to compare kind of the prior experience of these students with their initial conceptions, 8 of our students that held these kind of improper geometric or algebraic conceptions of tangency, they held these despite the fact that they never encountered a tangent line in a prior mathematics course. So they didn't learn about tangent lines to circle in geometries, or they didn't learn about tangent lines to parabolas maybe in algebra. Now, in addition, 5 of those 8 students held these improper conceptions without ever encountering tangent lines in another setting. Now, the conclusion that we drew from this was that, well, then they must have developed these misconceptions about tangency within their calculus class. Now, when we moved forward and at the end of the study, we kind of re-asked them to define a tangent line. We had a reduction in the number of students with these improper local or global conceptions of tangency. So these misconceptions such as saying a tangent line is only touching a function once, or it's only crossing, it doesn't cross over a function. Those kinds of misconceptions were reduced from 9 to 5. So 4 students removed those misconceptions from their definition of tangency. And this supports prior findings in the literature by Biza that visual examples of tangency are effective in creating cognitive conflict. And that is definitely something we saw throughout our study. However, some of the changes were not always positive. We had a few students that, originally had stated, didn't include any condition about it not being possible for there to be a tangent to a linear function. But when they actually saw a tangent drawn to the linear function, they added this into their definition. Now, of course, that's not the case. Linear functions do have tangent lines. They would just be the function themselves. But many of our students, and we had 3 students in total who did this, they saw the tangent to a linear function and they decided that that's something that should be excluded. So our changes in students' concept images were not always productive or positive. And an additional thing to add here is no students who did not initially mention slope or derivative added this to their final definition of tangency. Now, one theme that we analyzed were what were students' thought on this question. So can there be multiple tangent lines at a single point? So for the most part, student responses to this question were mostly in line with their final definitions. So students who define the tangent line according to the derivative or the slope would have responded no to this because there's only going to be one derivative or one slope at a point. However, students who did not define a tangent line in that way, maybe they defined a tangent line as a line which touches a function at a single point without crossing over it. Those students did accept that there could be multiple tangent lines to a single point. And notably, every student who did not mention slope or derivative in their final definition accepted the possibility of multiple tangent lines at a single point on a function. So it seems like whether or not students mention slope or derivative in their definition, that's a really good kind of measure here of their understanding of the tangent line. Some examples here where students drew multiple tangent lines to a single point, the one on the left and the one in the middle. Here they drew multiple tangent lines to a parabola. They believed in this case that these lines would only touch the function once without crossing over it. Now, that's not actually true. For example, this one on the left, only the horizontal line to that point would touch the function exactly once. But in the student's mind, these lines here touched once and did not cross over. To see a more accurate example here, this one on the right, in this case, the tangent lines that the student drew in here actually would only touch that point once, and they would not cross over that function. Now, another theme we took a look at was improper language use among students in our study. So there's kind of a tendency often to describe tangent lines by using words such as just touching, barely touching, or hugging. Now, of course, these words aren't well defined mathematically. And in our study, we had 3 of our students actually use that kind of language. And interestingly enough, none of these students noted any relation between the tangent line and the derivative or slope of a function. So it almost seems as if they're using these words because they don't have a better way to describe how a tangent line is actually behaving. They can't describe it in terms of the derivative or the slope. So they use these phrases, just touching, barely touching, phrases like that. Now, some takeaways from this study. Well, first of all, our study demonstrated the ability of these kind of visual examples of tangency to create cognitive conflicts in the students. I mentioned earlier that the number of students with these kind of improper algebraic or geometric properties in their definitions, we were able to reduce that from 9 students to 5 students. So because of the effectiveness of these visual examples, the fact that many textbooks are lacking when it comes to visual examples of tangency, they tend to over-rely on tangents to circles or parabolas for their visual examples. This might contribute somewhat to students' struggles with this topic. So because of this, teachers should try to incorporate a wide variety of examples on tangency to increase student exposure to various properties that tangent lines can have. Now, the fact that 5 of our students held these kind of improper algebraic or geometric ideas about the tangent line without ever learning about tangents in another class suggests that these ideas can take root or can originate from a calculus classroom. So factors in a calculus classroom that might contribute to this could include an improper use of language, using words like just touching, barely touching, and again, an over-reliance on a few visual examples of tangency, so tangents to parabola or tangents to a circle. Finally, our study supported Wiener's argument that students often reason directly from their concept image rather than from their concept definition. Our students were, pretty quick to change their definitions if they saw something on the paper that they didn't agree with, or something that they realized, hey, I think this actually should be a tangent line, but according to my definition, it isn't. So students really don't seem to use their definition as the definitive factor as to whether something is a tangent line or not. This points to the importance of actually helping students to develop a proper concept image. And again, a good way to do this is through a variety of examples of tangency. Now, finally, to talk a bit about our further research, we're currently planning a follow-up project that in which we intend to analyze in-service mathematics teachers' conceptions of tangency in a very similar way to this study. Our motivation behind this was, we saw that, or we concluded that these kinds of improper ideas about tangencies can develop in a calculus classroom, as well as, in earlier classes like geometry or algebra. So we wanted to learn, what do teachers, people who are actually teaching the subject, what do they know about tangency? What kind of ideas do they hold about tangency? So that's going to be it for our presentation. So thank you so much for taking the time to listen to it. Have a nice rest of your day.